All right, welcome everyone. Let's give it one more minute just so people can continue trickling in. If you didn't read the message, this is being recorded, so don't say anything you don't want someone to hear. All right, let's go ahead and get started. It is my great pleasure to introduce the next in a recurring series of the Advances in Science and Engineering enabled by ECP Applications breakout sessions at the annual meeting. This is one of my favorite things we do because we really unshackle the PIs to speak about what's exciting about their applications to them and not just force them to speak to how painful it is to make them run on our next machine. So this session, we have Mark Gordon from the Games Project, Jackie Chen from Combustion-PELE, and Danny Perez from EXAALT. And each speaker is going to speak for about 25 to 30 minutes. It's the 90-minute session, but we will stay on after if people have more questions than we have time for in our Q&A period. So let me go ahead and let Mark take it away for games. And please feel free to ask questions in chat, and I can ask them myself at the end, or we can interrupt at the Q&A session. Go ahead, Mark.
Okay, thanks, Eric, and thanks everybody for coming to listen to me. So I'm part of the lead PI for the Games ECP project, and there are 6 institutions listed here. We are roughly an equal mixture of computational chemistry people and computer scientists, and we've been working together for a long time. Of course, 5 or 6 years on ECP, but also before that, most of us have worked together on DOE and DOD projects. So it's been great fun. And I have to say, and it's not just because Eric is listening, that ECP has been the most fun and gratifying project I've ever been on. It's just been a great deal of fun. So I'm going to tell you a little bit about what we do. Oh, there we go. Okay. So the motivation for what we do is heterogeneous catalysis. And that basically means that the catalyst itself is typically in the solid phase, and the reaction that's going on is in liquid and or gas phase, usually in solution. And so the catalyst is called an MSN, or mesoporous silicon nanoparticle. They are synthesized in Ames lab. And they're highly selective catalysts, which means that they keep stuff out that you don't want in the pores and only allow the good guys in. And so we have to deal with the pore itself, which is very big, tens of thousands of atoms, plus the catalyst groups, which are these blue guys here, plus gatekeepers that keep the bad guys out, plus a solvent. Which is inside the pore. So it's very complex, tens of thousands of atoms, as I said. And so we need novel approaches, and novel, meaning both methods and algorithms. So basically, our target is to use 3 levels of theory: Hartree-Fock, which is the lowest level of theory, second order perturbation theory, or MP2. And I'll tell you more about the scaling of these things in a couple of slides. And coupled cluster theory, which is the highest level of theory that we use in this project. We have a model of the mesoporous silica nanoparticle, which is roughly 1,800 atoms, 15,000 basis functions, for those of you who know what that really refers to. And then on top of that, we have to add the solvent. And so we end up with the smallest system, which is sometimes called the base problem, around 15,000 atoms, which is a lot of atoms. So it's huge computational costs, huge memory demands, and poor scalability in the sense of how the calculations scale as a function of the size of the system. So our approach is to make these kinds of methods more amenable to computations by adding 3 components. One is fragmentation, which means you split up the system into some number of fragments, each of which can be done independently on different cores or bunches of cores. And then we add GPU, of course, and that I will tell you a lot about what we accomplished with GPUs. And then we add something called the RI, or resolution of the identity. And the resolution of the identity is a very accurate approximation, but nonetheless, it's approximation. And that makes the entire calculation less computationally demanding, and most importantly, for the highest level of theory, less memory demanding. So the method that we focus on is the effective fragment molecular orbital, or EFMO method, which is developed in my group. And you can think of this as kind of a mini body expansion, where you have a sum over the energies of each monomer or fragment. And then you have a sum over energies of all the dimers and pairs. And if you wanted to, you could go on with trimers and so on, but we stop for everything we're talking about today, we stop at the dimers. And I'll just mention, I'll mention this more than once, that the dimers are the big bottleneck, because there's n times n plus 1 over 2 dimers, and those are the heavy duty calculations. And then you take the system and you break it into fragments. And this is a very simple example of on the left of propanol, on the right of water clusters. And we have methods that allow us to break these apart. So the way EFMO works is that in the short range, meaning which is user defined, the calculation is done by whatever quantum mechanics level of theory that the user chooses. The long range, which again is user defined, is done by something called the effective fragment potential, or EFP, which is a very sophisticated model potential. So it's not quantum mechanics, but it's all derived from quantum mechanics. And there's an input parameter called RCut that determines essentially how many of those dimers are done by quantum mechanics and how many of them are done by EFP. So here's an example. I showed you, excuse me, a couple of slides ago, a picture of the 1800 atom, roughly 1800 atom system, model system. And that's the same exact thing that I'm showing you on the bottom right here. So that's 1738 atoms split into 32 fragments. Each different color here is a different fragment. And what I'm showing you is a series of systems that are that lead up to the whole 1738 fragments. And that's what we use. So we use these 6 different systems of increasing size to do benchmarks and understand how the scaling is working. And again, these MSNs are very selective catalysts for a variety of reactions. I won't have time to talk about the chemistry today. So the RI approximation, I mentioned this, and it's very important, very central to what we do. It stands for resolution of the identity. And what it allows you to do is take these 4-center 2-electron integrals, PQRS, which are a main bottleneck in the calculations that we do, and approximate these in terms of 3 centers. So it's an approximation, and I can show you, I will show you toward the end that basically you're giving up almost nothing by making this approximation. And the bigger the system it has, the less you're giving up. And what I mean by that is on the order of, in chemistry or physics or materials terms, you're giving up basically tenths of kcals per mole, which is really within the experimental error. So this is really not a very, it's an excellent approximation. All right, so this is basically, for those of you not familiar with quantum chemistry, here's the workflow in quantum chemistry. You pick a basis set, a set of atomic orbitals, then you do a bunch of integrals, 1-electron integrals, which don't take very much time, 2-electron integrals that are, as I said, one of the main bottlenecks in our calculations. You feed these integrals into the Fock matrix and then do a Hartree-Fock calculation, which is an iterative process. And that spits out a wave function in terms of orbitals. And those orbitals are then used to build second order perturbation theory, or MP2, that scales on the order of n to the 5th, or RIMP2, which reduces the scaling down to approximately n to the 4th, where n is the size of the system. And the highest level of calculation is coupled cluster theory, CCSD parentheses T, and that scales on the order of n to the 7th. It's very, very demanding. And I'll come back to all of this in the next several slides. So a major component of what we do is to transform or transition the algorithms, many of the algorithms in games and Chem two GPUs, and we've actually been doing that for quite some time, predating ECP, but ECP has certainly made it a lot easier for us to do this, and that's been part of the great fun of participating in ECP. And we do this in two different ways. One is direct GPU coding in CUDA or HIP or DPC++, and we have several of the functionalities working on all three of these. Working in quotes, it depends on the hardware and software issues with the various systems. And the other approach is offloading of games Fortran, so existing Fortran code, offloading with modifications, of course, using OpenMP. We're taking both of these directions, and I'm going to tell you results without focusing too much on which of these pathways I'm talking about, because we've had great success with both of these, and there's pluses and minuses to both. Okay, so the fragmentation approach, it means you start off here on the left with some system you want to study, and I'll talk about some systems later on. And you fragment it in some number of fragments, and then you use something called the Generalized Distributed Data Interface, which is kind of analogous to what the Chem people used to call GA, or global array tools. And you split, that allows you to split the fragments into groups, subgroups. And of course, each group can then be calculated independently, and that makes it embarrassingly or coarse-grained parallel. And then each node, if you've written the code itself, the method itself, like Hartree-Fock or MP2 or coupled cluster theory, as parallel code, then you can have multi-level parallelism, which is of course what we have. And so this is done on the fragments and on the fragment pairs. And again, I'll mention that the fragment pairs are the big bottleneck, because if you have n fragments, you have n times n plus 1/2 dimers. And so that's where the heavy duty computation comes in. Here's a really simple example. This is a calculation that's run on a local Iowa State computer called Nova. So it's really pretty small. 112 atoms is very small compared to what I'll show you later, but it makes a point that's kind of interesting. And that is that what this table on the upper right tells you is, as you go from full RYMP2 to splitting up the work between quantum mechanics and EFP, what do you gain and what do you lose? So our cut here is 2, that's the default in games, or 1 or 0.3. And you can see that the wall time for the full calculation is about 255 minutes. But if I just use a default R cut, it's already down by a factor of roughly 8. And if I make R cut smaller and smaller, you gain something, but you don't gain a lot. And so the sweet spot really is R cut equal to 2, because that gets you the most gain and the least amount of error per fragment. The error doesn't change all that much for this system as a function of R cut, but remember, this is only 112 atoms, and we're really looking at tens of thousands of atoms for our real application. And so what you'll find is that the sweet spot is around 2 or maybe 1.5 for R cut. All right, so here's the MSN. This is the same 1738 atom system I told you about before. The guys hanging here down into the pore, those are the catalyst groups that have to be included. This is the bare MSN cluster, and then we have to add solvent. And so going from here, you can see the outline of the MSN here, and all the other little guys there, those are water molecules. And so that's 4,642 waters. And so what I'm showing you here is the scalability of EFMO on the MSN. This is using Hartree-Fock, and you can see it scales really well as we go up to roughly 1,600 nodes. So we're pretty pleased with that. Another really important point is that I've got it underlined here. Chemistry is local. Whoops. Chemistry is local. And so what I mean by that is that you have to have all these environmental effects present, but the actual chemical reaction is really localized on a relatively small amount of the system. And so that means you can introduce what's called multi-layer EFMO, which means that you have one layer which includes the bulk, and another smaller layer that is where the chemistry is happening. And so you can see in this example, that if you have 5 fragments, 1 layer, that it's costing you around 6,000. I think that's minutes. 28 fragments with a full ring, you can't even do it with a single layer. But if you split it up in so that the bigger layer is Hartree-Fock and the smaller layer is MP2 or RIMP2, then for 5 fragments, the cost goes down. And for the 28 fragments, you couldn't even do it with a single layer. Now is feasible, even though it takes quite a bit of time. All right, so here is scalability for the GPU, MPI, OpenMP, combined RHF. This is a cluster of 569 water molecules. And what I'm basically showing you here is the scalability is really very, very good as you increase the number of V100s on Summit. Here's a comparison between GPU and CPU with the RIMP2 energy. The CPU is the blue curve and the GPU is the orange curve. And this is a function of the number of basis functions, and you're seeing the wall time on the left. And this is basically, well, I won't dwell on the basis sets because maybe not everybody's familiar with basis sets. And it's being done on a series of carbon clusters, so basically fullerenes. And you can see that as the system gets bigger and bigger, the GPU gain is better and better. And that's kind of what you want to see. And here's a GPU RIMP2 on even bigger systems. This is up to 6 V100s. And again, you see the ideal speed up is the black curve. And as you get to bigger and bigger systems, blue to green to red, get closer and closer to very, very exciting for us. And now here's EFMO RIMP2 for the MSN and water. Now we're going up to 4,600 roughly V100s. And you can see this is the same kind of 2 scaling curves, except now much bigger system and much more V100s. And again, the ideal speed up is this kind of grayish line, and RIMP2 is the red. And you can see it's almost perfect. By the time we get up to 4,608 V100s, it's probably starting to run out of work a little bit. All right, so now I want to talk a bit about coupled cluster theory. Everything I've showed you up until now has been Hartree-Fock and second order perturbation theory within the RI approximation. So the RI approximation I explained a little bit before is a way of reducing the amount of work you need to do and the amount of memory you need for doing these electron repulsion integrals. And so that reduces the memory demand for coupled cluster. So I should explain that CCSD parentheses T means coupled cluster with single particles and double particles, and then an approximate way of doing the triples. And the triples are really important. If we don't have the triples, we're not going to get accurate energetics. So the RI approximation reduces the memory demand, which is a very big deal with coupled cluster theory because the memory demand is very, very high. Leads to improved parallel efficiency by allowing a more efficient factorization of the coupled cluster. And the MPI OpenMP parallel CPU-based RI CCSD T allows us to do 60 to 80 atoms, which is a lot. I mean, if you do a standard couple CCSD parentheses T calculation using most computer codes that you can get your hands on, you're not going to be doing 60 to 80 atoms or 1,000 to 1,200 basis functions unless you do something like what I'm describing. And then on top of that, we go to offload that onto GPUs, and that raises the 1,000 to 1,200 basis functions up to about 1,800 to 2,000 basis functions. So this is a major step forward. And the calculations that I'll show you in the next 2 slides were all done on Summit. So now before I go to the next slide, let me just remind you that the CCSD part of the calculation refers to single particles and double particles, and the triple T refers to triples. Because each of the next 2 slides will show you a little bit about CCSD and a little bit about triples. So what we find before I go to the next slide is that as you make the problem bigger and bigger, the the calculation is increasingly dominated by the triples, by this parentheses T. Interestingly enough, it's easier to make the T part parallel than it is to make the SD part parallel. So that works in our favor. So this slide summarizes the amount of wall time gain when you make the CCSD part of the problem parallel using the RI approximation. And here, what I'm comparing here is CPU to GPU, and you can see a speed up anywhere from 3 to 7. So on the average, the speed up is 5. And what I'm listing here, without going into any details, is that is the 3 biggest bottlenecks in couple cluster calculations. And so if you average these 3, say 5, although sort of thing except triples. This is a triples correction, and what you're seeing here is a comparison of the CPU on the red curve and the GPUs on the blue curve. And again, you can see the speed up is around 3, a factor of 3, so not quite as good. But now you're getting a speed up of 3 on the most demanding part of the calculation. And so what we find is that using multiple GPUs is really very, very important for these kinds of calculations. All right, so let me introduce you to something that's really interesting, and it's something that we have a very nice paper on just last year. This is called composite methods. Composite methods were introduced, I would say, 40 or so years ago by multiple groups. And what it means is that I want to do a calculation on some very high level of theory, let's say couple cluster theory, with a very large basis set because I want very accurate answers, but I can't do it. It won't fit on the computer for whatever reason. And so what one does is say, let's suppose that improving the basis set is independent of improving the level of theory. And if that's true, and it turns out to be a pretty good assumption, then you can do a low level of theory called LL, and with a small basis set and with a big basis set. And so the difference between these two, the green one and the orange one, is the basis set correction. And then you can do the high level theory and the low level theory with a small basis set, and that gives you a level of theory correction. And what I really want to do, but can't do because of computer demands, is the high level of theory with a big basis set, but I can guess that by assuming that this basis set correction and the level of theory correction are independent of each other. And that's been shown by many workers now that that's roughly true. And so there's a very well-known and very popular method called G3, which was due to John Popel many years ago, and it's still very popular today. And the high level of theory is CCSD parentheses T, and the low level of theory is MP2. And what we've done is replace these with the RI variants. So now the high level is RI CCSD parentheses T, and the low level is RI MP2. And then let's see how we do. So how we do means, what do we gain in terms of speed and memory? What do we lose in terms of accuracy? And so this is the accuracy slide. And basically, it's a little hard to read, but basically it lists a bunch of molecules. So a subset of the ones we use to test. And what we find is that the mean average error relative to experiment is about 1.5 kcal per mole, and the standard deviation is about 1.9 kcal per mole. And that might not mean a lot to everybody in the audience, but what I'll tell you is that that's roughly the same as the original method. So by replacing G3 with RIG3, we basically give up nothing in the hundredths of kcal per mole, which is way within the experimental error. So the performance, this is the accuracy. Sorry, this is the performance. And you can see that with RIMP2, for all these molecules, the MP2 is much more expensive than MP2. And same thing is true with coupled cluster theory. And as I told you, with coupled cluster theory especially, the memory demands are what really kills you. This is shown in a very nice paper 20 years or so ago by Alistair Rendell and his group. And so the memory saving is really a big deal. All right, so I have 4 more slides, and I'm going to, maybe 5 more slides, and I'm going to end on some go back to scaling on Summit. So we have done, I'm going to show you 3 or 4 slides. And this first one is calculations on a sequence of polypeptides. They're shown over here. And the biggest one is 750 of these polypeptide units, 45,000 atoms, 180,000 electrons. And this biggest one, we use essentially all of Summit. And 27,600 V100s, you can see it across the top here is a number of GPUs. Very good, strong scaling. The parallel efficiency is roughly 90%, which we're very happy with on the 2 largest numbers of nodes. This work appeared in a paper last year in JCTC. The second problem I want to show you about is on ionic liquids. So ionic liquids, kind of like it sounds, are systems in which the positive ion and the negative ion retain their identity when they're together. So they don't undergo proton transfers. They don't create a neutral system. They are actually ionic liquids. And it's become very popular over the last, I would say, 15 years or so, because they're very benign or green solvents. And some of them, not the ones I'm showing you here, but some of them is very attractive to NASA and to the Air Force because they turn out to be very effective and green fuels as well. So these are, okay, I've got just a couple more slides. Thank you, Eric. So the biggest system, which is this one with the arrow, has 146,000 atoms, 623,000 electrons. It boggles my mind still to even think of that number. And you can see that the strong scaling is really very, very good. And we had to do this in bunches because of the time limits on Summit. Here's the weak scaling on the same system. So this is the biggest system that we did, which is up here in the upper right, has a weak speed up of around a factor of 940 or 30x compared to the 32 nodes. So we're really very pleased about this. Okay, so next steps, we are, one downside of the CCSD parentheses T method is you cannot break bonds correctly with it. And my colleague at Michigan State, Piotr Piecyk, has developed something called CRCC23, and we are developing the RI for that, which will then be offloaded onto GPUs. Then we can break bonds correctly in big systems, which is very important if you're going to actually do catalysis. The composite methods we're working on improving by using machine learning. I didn't have time to talk about that at all. Energy gradients is important because if you want to do geometry optimizations or molecular dynamic simulations, you need energy gradients. And then finally, we're working on open shell and multi-reference methods to enable bond breaking in photochemistry. And finally, this is my thank you slide, especially, of course, to the Department of Energy and especially ECP. And these are the people who did all the work. So Sarome Liang is at EP Analytics, a small company. Giuseppe Barca is at Australian National University. He is an assistant professor. Jorge and Melissa are graduate students. Tussaporn and Peng and Bu are all staff scientists at the Ames lab. Depayan is a postdoc. They're the ones who did all the work. And I didn't mention Bryce, who's also a student. They're the ones who did all the work. I'm just a mouthpiece. So they really deserve 99% of the credit, and I thank them all. And thank you for listening. And thanks for inviting me, Eric.
Thank you very much, Mark. Please imagine everyone is applauding. It's hard to really reproduce that on Zoom.
I know.
We have time for one quick question. If someone would like to either raise their hand or just unmute and ask it. And I have one if people don't, so.
Go ahead.
Yeah. So the thing I find most intriguing about the fragment method is it seems like it offers some unique opportunities to sort of break the work up in a way that could work really well for the system.
Yep.
What is a typical number of GPUs or compute nodes per fragment? Is it possible to get it so that fragments could fit on a single compute node or a single GPU? Because it seems like that would have big advantages.
Yes, it is. It depends. So I mean, I guess the answer always to a question like that, Eric, is it depends. And so if we're doing something like water clusters or ionic liquid clusters, like I showed you in the last few slides, then you can design how you define a fragment so that it fits on a node. With the MSM, it's a little bit more challenging because you don't want to make a fragment so small that it's not meaningful anymore. So with something like a water cluster, you can say, well, my fragment is 1 water or 4 waters or 8 waters or 16 waters. Any of those really make some sense. With ionic liquids, it's the same thing. But when you're breaking covalent bonds, which is what we're doing at the MSN or the polypeptide, it's a little bit more difficult to design it. But the answer is yes, and it depends. GPUs on the memory that's available per node. So the answer is yes, but it would take some careful design.
Understood. Thank you very much, Mark.
You bet.
All right, our next speaker is Jackie Chen.
Okay, I think Mark has to unshare so I can share.
Okay, I think you should be able to do it now, Jackie.
Okay, thanks.
Great.
Okay, let's see. Put my talk in presentation mode. Can you see my talk?
Yep, looks good.
Okay. I'm Jackie Chen. I'm the PI of the Combustion-PELE project, and I'd like to acknowledge our large team and we've worked together very effectively over the last 6 years and developed a lot of friendships, and we bring to the table lots of different expertise that we need in this project, including algorithm methods development, software development, chemistry expertise, multiphysics expertise in sprays, thermal radiation, and some computer science expertise. And so these labs are Sandia, NREL, Oak Ridge, Argonne, and we have some university collaborators at University of Connecticut, Tianping Liu, and at MIT, Bill Green. The codes that we're developing, PELE, are mature enough now that they're actually being used not only within our team, but also with our collaborators from around the world. And so what I'd like to do in the next 30 minutes is focus on a few science vignettes that have been enabled by PELE. And I would like to defer in a second part of this talk to Mark Day, who will be speaking on Thursday in the afternoon to talk more about scaling, performance scaling on machines like Summit, Crusher, and Perlmutter. So our goal here is to develop 2 codes in this suite, PELE-C and PELE-LM X for compressible and low Mach flows, respectively. And these have been the 2 main centers of development in our project. They're both reacting flow PDE integrators that are built on top of the AMRX library. So the AMRX library has provided things like data structures, parallel data models, host device memory offloading management, and so on. And the codes feature block structured AMR with finite volume. PELE-C is a compressible formulation, uses Godunov-based explicit integrator for hyperbolic and diffusive transport, and a simple higher order run-to-Kutta method of lines for explicit chemistry solve. It also uses VODE for implicit chemistry if we have stiffness in the mechanism. PELE-LM, on the other hand, implements a low Mach formulation where the acoustics are filtered out from the system. And so if we're not dealing with high compressibility or shocks, we don't need to march along at very small time steps. And so the time steps can be much bigger. However, the flow field must evolve on a constraint, an algebraic constraint of a constant thermodynamic pressure. Here we use an approximate projection scheme to enforce this. And as a consequence, this needs the solution of a linear elliptic system at each time step. And because of the increase in time step, the diffusion is also solved implicitly and is coupled tightly with the reaction terms, which are solved, as I mentioned earlier, with an implicit ODE integrator. Our our development path over the last several years has been that PELE-C, being the easier of the two codes, typically leads PELE-LM in the implementation of new physics terms. So we have a lot of multi-physics in this project. As I mentioned, sprays, soot, and thermal radiation, and we're also starting to add plasma physics. And it also leads in the implementation of programming models for new architectures. The time step in PELE-C allows simpler testing for new features, and as we settle on efficient implementations, then they're moved off into PELE-LMX. So our KPP2 challenge problem is around looking at in-cylinder fuel injection and auto-ignition processes inside of an engine at realistic dual fuel reactivity control of compression ignition conditions. The simulation will demonstrate key physics capabilities, high pressure, multi-pulse fuel injection, low as well as high temperature ignition chemistry involving a range of fuels with different reactivity, including flame propagation and auto-ignition. And we're also doing this in a geometry-driven way so that we can get the correct mixture preparation inside of an actual piston bowl geometry in a low Mach hybrid DNS-LAS setting. The case that we're looking at involves kinetically controlled processes and turbulent combustion. As I mentioned, ignition, extinction, emissions, and we have to understand some of the controlling engine processes, including knock, diesel injection, and lifted flame stabilization. And while fully resolving the realistic conditions, the thermochemistry in an engine cylinder is still beyond reach, even with exascale computing resources. We've created a pragmatic strategy that allows us to glean fundamental scientific insights while also preparing to address these practical combustion-related problems for engine designers. And so some of the science questions we're interested in answering are shown here on the right. In other words, we want to know, what is the distribution of reactivity by imposing dual fuels or single fuel with multiple injections and inside of the cylinder? How are the gradients in reactivity affected by how you mechanically inject the fuel? So in these cases, a lot of it's direct injection, impulsively forced jets. As I mentioned, composition and the duration, the dwell time, and timing within the motion of the piston in the cylinder determines these reactivity gradients. And then how does the reactivity distribution affect emissions formation? For example, pyrolysis near the walls and soot generation. And are there identifiable kinetics, especially these days with alternative fuels that are carbon-free, carbon or neutral carbon-free, carbon fuels that can help expand the operating map for these engines? So in the last several years, my postdoc, Martin Reith at Sandia, has worked on endodecane multi-injection DNS related to heavy-duty diesel engines. And this was several years ago before a lot of alternative fuels come to the fore. And so he simulated simplified gaseous pre-vaporized jets downscale to compare to ongoing experiments at the engine labs at Sandia CRF. He reduced the Reynolds number, maintained the same turbulence chemistry interactions through the Domkoehler number. And these were low Mach jets simulated with PELE-LM with a 35 species endodecane mechanism that represented both low and high temperature ignition and up to 3 billion grid cells. And at that time, several years ago, it was run on CPUs on Cori at NERSC. He considered two cases with different ambient oxidant temperatures of 750 and 900 Kelvin at 60 atmospheres. And the data was used to glean insight into the physics behind what people observed experimentally but couldn't explain. And so some of these questions were, how does first stage combustion products, intermediates of the cool flame, affect ignition, subsequent ignition of the hot ignition, or of the second injection, sorry, which might be mixing with high temperature products from the first injection combustion or with radical intermediate species. And how does this affect flame propagation into this autoignited mixture? The data sets that were published were also used by modeling groups in Germany, in particular one by Christian Hasse's group, where they looked at LES modeling based on multi-injection DNS from this PELE-LM data. And I should also mention that Emmett Hawks and Delacote, together with Mark, have also looked at single jet endodecane injection systems. So what has changed in the last few years, and where are we headed with this project, and where do we see using the tools that we develop in this project in the future? So what has become extremely important is decarbonizing transportation. Transportation, especially for hard to electrify sectors that aren't going to be, it's not going to be feasible to run on batteries. And so these include things like marine ships that transport goods across the Atlantic Ocean, to rail applications, to gas turbines for propulsion, so the airplanes that we fly. And so there's a huge push within our country, as well as in Europe and Japan, China, everywhere, to develop technology challenges to address these challenges with large-scale adoption of these low, zero, and neutral carbon fuels to mitigate climate change. And so there's challenges both on the production side as well as on the end use utilization side. And so we envision that PELE is going to be able to contribute to both of these technology aspects. Just to illustrate, I'm showing here this National Fuel Jet Combustion Program referee rig for a gas turbine combustor that's at the Air Force Research Lab in this picture on the top. And you can see the flame in operation here. It's very luminous here. It's lifted. The flame stabilizes away from the nozzle. It has a very, very complex flow field involving complex mixing layers with multiple recirculation zones. The inner recirculation zone, you can kind of see this in the picture of the streamlines on the bottom, that's recirculating hot products of vitiated gases containing water and some radicals back up to and mixing with the shear layer where the combustion is occurring. There's also an outer recirculation zone near the wall. So there's also recirculation flame wall interactions that are important here. And a lot of the CFD predictions of the local mixture velocity temperature are essential, but they're confounded by a lot of uncertainties currently about heat transfer, wall temperatures, heat fluxes, and turbulent mixing in general. And we know that the amount of mixing and the residence time that a fluid parcel spends strongly affects both its combustion rate as well as emissions like soot. This also comes in typically as a liquid spray, so there are also issues associated with atomization and vaporization and its influence on cool flame, low temperature ignition, as well as high temperature ignition. So just to illustrate the complexity, the National Jet Fuels matrix is shown here from a publication by Hang et al. In 2018. You can see in this table that A1 through A3 are the petroleum-based jet aviation fuels that we're familiar with, and then C1 through C9 are these alternative non-petroleum-based fuels. A lot of them are alcohol to jet, for example, and they range in greatly in their properties shown on the right: densities, freezing points, hydrogen content. And I want to pay particular attention, draw your attention to this thing called the derived cetane number. This is a measure that is inversely proportional to the ignition delay. And so a low cetane number like alcohol to jet, or a fuel that's simpler that we're all familiar with, methane, is very difficult to ignite. On the other hand, at the other extreme limit where you have high derived cetane numbers, a fuel like endodecane, which stands in for a fuel like C9 here, based on hydroprocessed esters and fatty acids, is going to be much simpler to ignite. So the trick is, as I pointed out earlier, is how to combine the injection or blending of these fuels so that you can get the chemical properties to work in concert with your engine. And this is just to further showcase that the SAF type, the sustainable aviation fuel type selected has a big impact on lean blowout in aviation engines. So you can see in this chart on the right, for 7 out of 8 different experimental rigs, that you get much greater lean blowout at low cetane numbers and much larger variability, but at the blowout decreases as you go as you increase the ignitability or cetane number. So this begs the question, research questions about how to change, what changes the cetane number or ignitability due to the flame structure. How does it affect the flame speed? How much of lean blow off in an aviation engine is dominated by auto ignition? Is it just premix flames or auto ignition assisted premix flames? How does the ignition tendency affect premixing and soot formation during takeoff and cruise? And how does the upstream cool flame behavior affect all of this evolution? And so we think that the aviation engines are, gas turbines are extremely complicated, and it would be great to have a simplified configuration with better well-defined ambient gas and fuel conditions. This is a Sandia constant volume spray vessel that's been used for heavy duty IC engines, but could also be adopted to look at aviation engines. And this would allow us to have very controlled compositions that mimic the vitiation or heating of ambient recirculation zones and its effect on the combustion rates. And so to this end, we've started to perform dual fuel ignition, and we're using endodecane injection, a single injection, which has a cetane number of 87, similar to the C9 SAF fuel I just showed you. And we're injecting this into a lean methane air mixture, which is hard to ignite. It has a low cetane number similar to GEVO alcohol to jet C1 SAF. And this dual fuel combustion is a promising strategy to help reduce emissions like soot. And the main charge here, as I said, is methane, hard to ignite, and we need the endodecane or some highly ignited fuel to get this thing to auto ignite. Again, we went with the simpler pre-vaporized jet initially. We downscaled to match experiments. Experimental Domicole numbers preserved at 60 atmospheres, the ambient methane air mixtures at 900 Kelvin. The pre-vaporized endodecane is at 470 Kelvin. The low Mach jets were simulated with PELE LM on Summit. In this case, we used a 54 species endodecane skeletal mechanism for both first and second stage ignition. And the injection duration was half a millisecond. So here's what happens. What we see if you go in time from left to right in terms of the evolution of the temperature field, we see that the cold 470K pre-vaporized endodecane air mixture, after it's injected for half a millisecond, ignites around 0.6 milliseconds. You start to see the temperature go above 1000 Kelvin, as shown by these cyan-like colors. The load, they start to ignite, but if you compare these plots with what happens if you didn't have methane in the premixture, but just air, the low temperature ignition is delayed. So it occurs almost twice, it takes twice as long to ignite with methane addition as it does without methane addition. And then we see high temperature ignition, 2000 Kelvin, shown by these red colors, occurring about at 1 millisecond. And again, it is also delayed, as shown in the red homogeneous ignition plots without methane compared to with methane. Now, if the beauty of PELE with detailed chemistry is we can look at the evolution of intermediate species that are very difficult or impossible to measure. One of these is formaldehyde. This is a low temperature ignition marker. And you can see, again, moving across in time from left to right, you see that formaldehyde starts to form on the periphery of the jet where you have hot ambient plus methane. And then it propagates through a cool flame propagation into richer, colder parts of the mixture that help to bootstrap the harder to ignite colder fluid in the center. And there's still research questions as to what wins. Is it cool flame premixed flame propagation, or is it spontaneous ignition augmented by enthalpy and intermediates from species like formaldehyde? And then finally, formaldehyde is consumed by hot ignition. We also see another interesting low temperature species that's at the heart of the low temperature chemistry called Keto Hydroperoxide. It also, like formaldehyde, forms on the periphery of the jet. Regions that form keto hydroperoxide early feature low temperature ignition kernels and are characterized by a slight increase in temperature of about 50 to 100 degrees and formation of formaldehyde simultaneous with keto hydroperoxide. Once initiated, as I said, the cool flame low temperature ignition transitions to richer regions. This is seen in the conditional mean plot of formaldehyde plotted versus mixture fraction as a function of increasing time from blue to red. So you can see this wave. It ignites close to the preferred homogeneous mixture fraction, but then there's a wave that propagates towards richer mixture fractions as the evolution evolves. And then you can see also from a fuel consumption standpoint, during low temperature ignition, endodecane, shown in the fourth panel, is consumed throughout the jet, and its consumption rate is an order of magnitude larger than methane, shown here on the right image, where methane is mostly consumed on the periphery of the jet rather than over the entirety. And it's consumed in regions where it's helped along by low temperature ignition. And this is just shown quantitatively, looking at the consumption rate conditional on the mixture fraction, where the methane consumption rate is 10 times lower. I've multiplied, or Martin has multiplied this by a factor of 10, comparing it with the blue line, which is the endodecane consumption. During hot ignition, endodecane, again, here is consumed throughout the jet, this fourth frame. It is still an order of magnitude larger than the methane consumption, and methane is still consumed at the periphery of the jet in regions of high temperature ignition, where premixed methane flames are initiated. The interesting thing is when you look at the consumption rate conditional on the mixture fraction, there's a negative consumption, or actually production, of methane that's produced by the consumption of endodecane in the center of the jet. So where endodecane is consumed, methane is actually produced there. And so we're still in the midst of delving into the details of that interaction. But I'd like to say then that we've moved on, and these are liquid fuels. And so we've started to look at spray flame ignition with PELE-LM with our multiphysics spray module. So Landon and Marco and Martin have worked closely together to set this up. This is an equivalent thermochemical and conditions as the pre-vaporized case I just showed you, where endodecane is injected at 5 milligrams per second at 363 K, where it's still a liquid. The drop size here is 5 microns, and the injection speed of the spray is 30 meters a second. It has been scaled down from the original spray A. Same reaction mechanism as before, and the grid size on the finest mesh was 10 microns. This just shows the temperature plot on the right, and there's quite a bit of evaporative cooling that affects the mixture formation upstream of where it ignites. So again, we compared the spray case with the pre-vaporized case, and I have to say that the preliminary results show that there's not a large influence of the spray injection so far that we see. We see ignition, low temperature ignition occurring at about 0.5 to 0.6 milliseconds, similar to what the pre-vaporized case showed. We also see that formaldehyde appears on the periphery, as shown before, and then it migrates eventually towards richer mixtures, and at high temperature conditions burns on the rich side. Similar story with keto hydroperoxide. It peaks at low temperature ignition, starts on periphery, moves to the center through cool flame propagation, and then it is consumed entirely and disappears during hot ignition. Endodecane consumption rate is, again, mostly at the fuel jet center, whereas the methane consumption, as I mentioned earlier, is out on the periphery. So these are consistent results with what was seen in the pre-vaporized case. So what are our next steps? With PELE-LMX, we are extending these single jet calculations to a closed volume, simulating the full piston bowl geometry of auto-igniting endodecane jets into methane air. And so we've had to extend the low Mach algorithm to include time-varying mean pressure, including mass injection with AMR. We've also had to create utilities in PELE physics to help us handle turbulence injection of multiple inlets and more flexible restart capabilities for different mechanisms and different grid resolutions. We're also working on expediting the chemistry evaluation and have done some initial benchmarks to compare different chemistry methods, including magma batched dense direct solver that's available through sundials. So far, that's the fastest option. We're also looking at a chemistry compiler Singe that takes advantage of GPU warp specialization. And so we'll be optimizing that soon also on Crusher. And finalize the port of PELE-LMX onto Crusher for all of the major components, and got performance parity between an MI 250X on Crusher and one on Summit, one of Summit's V100s. And Mark will go into a lot more detail on the algorithmic developments and the performance benchmarks later this week. And so I'd like to just spend a few minutes saying that we want to also, we are also interested in data science out of necessity. So DNS takes full advantage of time-resolved 3D fields, but takes a huge amount of computing time and a lot of memory requirements. And so one of the challenges for us is the incorporation of detailed chemistry. We need it for accuracy, and a lot of the fuels, the sustainable aviation jet fuels, have very, very large chemistry. Very high dimensionality, orders of hundreds, and these are stiff ODE systems. And so this is just a chart showing the number of elementary reaction steps on a log-log plot versus the number of species. And so for a detailed model, and you can see that the blue symbols up to the stars indicate that the mechanisms are only growing in size and time. And so putting 1,000 species and 10,000 reactions into a CFD code is just insane and not possible, but reducing it greatly, you start to lose accuracy. And so there are methods out there that allow us to do skeletal reduced mechanisms for diesel surrogates or gasoline or jet fuels on the order of 100 species, 1,000 reactions. But there's still needs for reduced order modeling or digital twins for representing high dimensional chemistry. And so there's a need for high fidelity training data, but there's also a need to use in situ reduced order modeling. For example, here's one that we've been interested in working with Hassan Babay at Pittsburgh, University of Pittsburgh, and this is a dynamically by orthonormal decomposition, and it's based on a on-the-fly low-rank decomposition of the species transport equations without having to rely on training data ahead of time. And as shown in this figure, the DBO approach involves deriving a low rank approximation of the species vector. Using a SVD, singular value decomposition. Here, Y is the actual species vector. U, shown pictorially here, is a quasi-matrix whose columns are orthonormal spatial modes. Sigma T here is a reduced factorization of the covariance matrix. And V sub T is a matrix of transpose, is the matrix of orthonormal species modes. So unlike the standard PCA approach, a key difference here is that all three components, U, sigma, and V, are time dependent. They're not static and determined a priori from data. The reduction in DBO is achieved by extracting instantaneous correlations between the different species on the fly and directly from the species transport equation. The use of DBO-based ROMs eliminates the need to store the entire species vector, and it has the potential to scale and solve large-scale optimization problems. So without going into all of the detail, here are the equations for the DBO math. Shows 3 equations that you have to solve. 2 of them are ODEs, only 1 PDE on top of the on top of the normal conservative forms of the species transport equation. So in a typical DBO calculation, it relies on evolving the actual governing equation for several time steps, about 1,000 time steps that allows the reactive flow to develop. And as a result, the rank R based on the instantaneous PCA increases and the matrix sigma then becomes non-singular. And so we tested this concept out, this ROM out with a multi-stage ignition, which has got a lot of transients, both for the low temperature and the high temperature ignition, with the 52 species in heptane test case. And so this is a brief overview of some of the details, which I won't go into. Our initial tests were with the code S3D. As this is becoming more successful, we're going to migrate this over to PELE. And it does require some linear algebra operations using LAPACK, and very fine resolution. And so with this initial temperature hotspot in the middle, we see the DBO calculation. What we're showing here is the temporal evolution is shown by the different colored lines of temperature on the upper right, upper left, oxidizer, the peroxy radical representing low temperature chemistry, and OH radical representing high temperature chemistry that was observed using DNS compared with DBO. So DNS is the solid lines, DBO at each time instant are the dashed lines. And you can see that as you have low temperature ignition, which propagates outward into richer mixtures in the cool flame, and then later you have high temperature ignition, and then the formation of premixed flames that emanate from the hot ignition. It's remarkable the DBO is able to capture the entire transient ignition process. And the only slight problem that we see here is there are some spurious oscillations that appear. You can see that here at the very late stages in the OH profiles. However, these magnitudes are quite small. So overall, DBO, we tried it here with a rank of 30, so roughly about 40% less than all of the species, captures all the trends and the transients obtained with the full rank DNS. So it looks like to be a very promising approach. I won't go into all the details of the error analysis, which are shown here, that comparing the reduction of the DNS data based on the instantaneous PCA analysis. I won't go into these details, but just to say that the DBO error, you can see here, is on the order of 10 to the -3 when it settles out and plateaus at about 0.6 milliseconds.
But we're at time. If you could just jump to the.
Yes, so I'll just say that I think there's a lot of promise for PELE codes, both for calculations on exascale machines, and those calculations will be incorporate more complex workflows, including reduced order modeling. And I won't go into the other examples, but I can leave them or make them available to you. One of them is on high-speed hypersonic flows, shock systems involving oblique detonation waves, and several other vignettes on flows relevant to gas turbines for power generation and complex premixing and auto-ignition phenomenon inside of premixers and interactions with walls. So I'll stop here.
Fantastic. I hated to interrupt. That was fascinating. But let's go ahead and jump straight to Danny. And anyone who has questions for Jackie, just hey, if you want to hang out till after Danny's presentation, we do have time in this session. We could have questions after that. I think you might need to stop sharing, Jackie.
Okay.
But again, thank you very much. That was fantastic.
Thanks.
Okay, can you hear me all right?
Yeah, looks good. Take it away.
Great. Well, first, I would like to thank Eric, Andrew, and Jack for the opportunity to speak today. So I'm Danny Perez from Llano, and I'm the PI of EXAALT. So we're centered mostly around 3 institutions. So we have a big team at Llano, at Sandia, and we have domain experts at UT Knoxville. And we also have extremely valuable collaborators at NERSC, NVIDIA, and Argonne. So you can see that the team members here are color-coded. So we really have different skills and different backgrounds in the team. We have method development people, code development, code optimization, machine learning, domain science, and so forth. So today I won't say much about the code aspects. I will mostly focus on the overall challenges that we face, the methods that we use. I'll say something about our machine learning efforts, and then I'll give an example of an application that we can do with the code at the very end. So it's going to be quite light and at a high level. So if you have some more technical questions, feel free to ask at the end. So EXAALT is driven by molecular dynamics, and MD is a very simple numerical method. It's basically just a numerical solution to classical equation of motion for a bunch of atoms. So what you do is that you put atoms in a box, you compute the gradient of the potential energy of the whole system. That gives you the forces on the atoms. Then you can time step the forces with a simple explicit scheme, and then you just repeat this over and over, right? So all of the physics of the problem is in this potential V over here. So this is material specific, and it's meant to describe a specific material, metal, alloy, or whatever. Typically in classical MD, we don't solve a full quantum problem to estimate the potential energy of the system, although sometimes we do. But in the context of the talk today, all of the results I'll discuss were carried out with empirical approximations to this potential. So basically, you have a quantum mechanical energy surface that you can estimate, let's say, with DFT, and then you fit some kind of empirical approximation to it to get a potential here that's fast enough to do molecular dynamics. So what comes out of an MD run is basically a fully resolved movie of what all of the atoms in the system are doing. And what that lets you do is to resolve typical nanoscale evolution mechanisms by which a material might evolve under pressure, under temperature, under stress, for example. So you could look at defect, nucleation, motion, interaction, so on and so forth. So MD is really used all over the place in chemistry, in materials, and biology, and there's literally millions of papers out there that either use or refer to molecular dynamics. So of course, in ECP, our obsession is to parallelize stuff. So an interesting question here is to understand what can we do with molecular dynamics on a parallel machine. So most of the computational cost in an MD run is in the calculation of this gradient here of the potential. Very often for the systems we care about, the potential energy is short range. So it's a function of it's a local function of the configurations around each atoms in the system. So if you would have charges, that obviously wouldn't be true, but for the sake of our argument, assume we have something like a metal where interactions are short range. Then in this case, you can use kind of conventional domain decomposition methods to parallelize molecular dynamics. And that's something that has been done with great effect for many, many years. Of course, the downside of domain decomposition is that you have to communicate with your neighboring domains at every time step. So this is going to be efficient only insofar you have a lot of computational work to do compared to the amount of communication that you have, or if you can somehow hide the communication by overlapping it with computation. So now I'll kind of discuss the 3 different simulation axes that you might be willing to push over with a very large machine. So you might want to do larger systems. You might want to do more accurate calculations, or you might want to do longer simulations on kind of small systems. And of course, what's great with domain decomposition for a short range problem like this is that it weak scales perfectly. So if I double my system size and I also double this, the number of cores that I use to solve my equations of motion, then the parallel efficiency just remains exactly the same. And I can just keep going, make my system bigger and bigger. So I get weak scaling for free in a sense with domain decomposition. So if you give me a larger machine, I can do a bigger simulation without too much additional work. So another axis you might be interested in pushing if you have more compute, of course, is to make a more accurate simulation. And in the MD world, that's a nice figure that was done by Steve Plinton and Aidan Thompson a few years ago, where they track the evolution of the different functional forms that people use to approximate the potential energy of the system as a function of time. And as you see, these become more and more sophisticated, and so they become more and more expensive as time goes on. So this is a metric of cost of running a certain amount of MD time on a single core. Okay, so generally speaking, these get significantly more expensive with each new generation, and hopefully their accuracy also is comparable with the added cost of running the potential. So accuracy is kind of, well, from a computational perspective, having a more expensive potential is a good thing in terms of scalability, right? Because you have more work to do locally compared to the amount of communication that you have to do with your neighbor that essentially doesn't scale with the accuracy of your potential. So in principle, it's quite easy to do a more accurate simulation using more cores. It's kind of another weak scaling type axis that you have access to. And I'll point on that figure that there's a few points starting from 2010 that are shown in blue. And this corresponds to the point in time where so-called machine-learned interatomic potentials were introduced in the community. So before that, there was a lot of deep thinking and manual injection of physics in these functional forms that was done to reduce the number of parameters that needed to be fitted. And from 2010, people realized that you can come up with fairly generic functional forms that are extremely flexible, that in principle can fit a whole range of different physics without you having to specify it by hand. And in the context of EXAALT, we mostly work on the so-called snap potential that was developed at Sandia by Aidan Thompson and collaborators. So I'll come back to this machine learning aspects in a few slides from now. So at a high level, if you give me more compute, I can do more accurate simulations fairly easily, at least from the computational point of view. So what about timescale? So if I want to use a bigger machine to reach longer timescales, then I need to strong scale my simulation. So I need to throw more cores at the problem at fixed problem size. And of course, if you do that, then at some point, things are going to break down because you're going to upset your balance of computation to communication. And at some point, you're going to become purely communication bound. So for a cheap interatomic potential, this communication wall that you hit occurs somewhere at simulation rates of tens to hundreds of nanoseconds a day. So basically, no matter what the size of the machine that you have, you likely won't be able to exceed that wall here unless you have special purpose hardware, for example. But on general purpose machines, that's a pretty robust rule of thumb. And this is unfortunate because there's this big region here of the simulation space where, in principle, we have enough flops to carry out simulations in this regime, but we're just communication bound in a way that we cannot access that region. And that, unfortunately, that has been the case for many years, that we've reached this limit where we can do bigger and bigger systems, but we basically cannot do longer times no matter what machine we're using to do this. So as we can see, we have some asymmetry in the simulation space in terms of how useful a parallel machine might be to you or an exascale machine might be to you. And in EXAALT, one of our key high-level goals is basically to fill as much of this three-dimensional simulation space as we can by developing tools that would let the users dial in the size, the accuracy, and the time scale at which they want to run their simulations. So key message here is that in general, a bigger machine does not get you longer timescales, except if you're if your model is, your potential is so expensive that you can efficiently parallelize it over the whole machine, which is quite uncommon for empirical potentials. Okay, so I also organized the rest of my talk in these two vignettes. And one of them, I will come back to this accuracy question and whether we really get accuracy for free. And then I'll discuss more about the long time scale issue and the strong scaling issue and tell you about some of the methods we developed to get there. And I'll give you an example of an application that we carried out using these methods. So let's come back to the, okay, so before I jump to the accuracy, of course, to be efficient on a machine, it's not just a matter of scaling. You also want your kernels to be efficient running on a single computer, and that's on a single GPU, for example. And that turns out to be challenging for more complex potentials. So I don't have time to talk about performance here, but I just want to say that we have a crack team of performance experts that really pushed on optimizing our machine learned potential kernels to run extremely efficiently on GPUs. So if you're interested in these aspects, you can stop by the poster later today and we can discuss the performance aspects. So what I'll do now is go back to my first vignette on accuracy. And the claim was that basically a bigger machine lets you do a more accurate simulation for free. But that is only partially true, right? Because running the actual simulation is only a small part of our lives as MD practitioners. Usually the way things work is that we have some idea, or maybe a colleague comes with some experiments on a new material, and then we want to do MD to verify or to interpret their experiments. So then we have to go in the literature and see whether there's a potential available to do this. And even if there is, it might have been fitted to something completely different than the properties you care about. So you still have to validate it and make sure that you expect it to do a reasonable job for the properties you care about. So if it turns out that the potential is not great or that there's no potential at all, then you have to go in a dark room and think hard for a long time and come up with a new potential. Okay, and literally that can take months and sometimes even years to get a good potential. And then once you're satisfied with your potential, you go on your big machine, you do your runs, and you do some validation on the interesting things you saw, and maybe you have to go back to the drawing board and still improve your potential because something went wrong. So now if you give me a big machine, what happens is that I can run my simulations faster, or I can run my simulations at higher accuracy. So that's nice, but the thing that it doesn't remove is the need to fit this potential here. Okay, so we have some kind of Amdahl's law here where there's a part of the calculation that's really easily parallelizable, and there's a part of the whole workflow that's really not parallelizable because it involves a human staring at the result, interpreting this physically, figuring out what's going wrong, what can I do to fix it by either adding more data or tweaking my functional forms and so on. So an Exascale machine will really be nice in terms of making larger and more impressive simulations, but in the sense of the whole workflow, there's still a lot of work that falls outside of what these machines can help us do. So one of our stretch goals in EXAALT is to address this concern or this limitation by trying to move the whole workflow to the Exascale machine all at once. So even if you start cold without a potential, you would generate training configurations, run the DFT on them, fit your potential, validate the potential, and run your MD all in one allocation in the queue, where you just send this to the queuing system. And the dream is that it would do all of this for you. Okay. So the key here really is to learn how to create these potentials here that would be robust, right? So that they don't fall apart as soon as your MD run does something interesting and brings you to a new region of your configuration space. So again, we have a very nice team of collaborators working with us on making this dream come true. And I think we're making quite nice progress. But I'll just highlight one specific aspect where I think we made some very interesting contribution to the state of the art. So I talked about these machine learning based potentials before, and something that changed with this new generation of potentials is that they use very generic basis functions, and they have lots of them, right? So Sometimes you use a neural network to combine them, and there's a ton of weights, or sometimes so you just have a huge number of parameters that appear. So you need a huge amount of data to constrain these potentials to actually behave properly and not just fall apart when something is wrong. So now the worry is not so much that the functional forms are not good enough to capture the physics. The worry is that you need to find enough good data to constrain the models. So the typical mode of failure is that you fit a potential to some properties that you thought were important. You get very low errors, you're all happy, you go run. Then your MD run does something you didn't expect and just pushes the potential to a new region of feature space that you were not aware of, and then things go nuts. Okay. So a big key in being able to automate that whole process is to automate the generation of the training set so that you minimize the amounts of surprises that you might have when you actually run this to do some science with it. So our contribution here was to develop an automated method and scalable method to generate training data that would make potentials really robust and transferable. And the way we did that is by explicitly maximizing the information entropy contained in the data set. So the idea is that we can write an approximation of the entropy of the distribution of our training data in feature space, and then we can use this as an explicit objective function and just drive configurations of the system in such a way that they provide as much diversity as possible. And then we add this to our training set. So I, as a human, don't have to think hard about how can I create new funny configurations that wouldn't leave any hole in my feature space. I can just offload this to the machine and generates hundreds of thousands or millions of configurations without human intervention. And what we find is that it's really giving really good results in terms of achieving this robustness that we're really striving to. So what you see on this plot is basically a quad chart where we train and test the potentials on two different data sets. So either a handcrafted data set that an expert put together, or our entropy data set. So if you're interested in very high accuracy, then using a handcrafted data set is best, right? You put the configurations that are really like concentrated around the configurations you deem important, then you get low error, but only if you test your potential on other handcrafted configurations that look similar. If you try to extrapolate from that data set to our entropy data set, then things just completely fall apart, right? And this is the extrapolation failures that I was mentioning before. You can have errors that increase by orders of magnitude when you leave the support of your training data. So now with our entropy method, we get errors that are slightly higher, but they're really uniform all over the place, right? We can sample extremely funky looking configurations from our entropy data set and still get the same kind of low errors. And more importantly, we capture the energetic of the domain expert set without ever having had to inject some expertise ourselves, right? So we capture everything that the expert deemed important, plus a whole bunch of things that they didn't know might turn out to be important when you actually use this potential in production. So we're quite excited about this because it really lets you automate a big part of the workflow that's consuming a lot of the life of MD practitioners. So now I'll switch gears to the second vignette about strong scaling and timescales. So here the story was that with conventional domain decomposition, you cannot strong scale, so you cannot reach long timescales. So is there a way around this? Well, there's not a way around it if you're not willing to give something in return for this strong scaling. So what we're going to give in return here is the perfect continuity of the trajectories in phase space. So if you do an MD run in the regular way, you would see that all of your trajectories are perfectly continuous in phase space up to your discretization time step, of course. But in some sense, as a material scientist, most of the time, I don't really care about these micro details, right? What I care about is what is the topology in which my system is, where the defects are, in which configurations they are, what spatial position are they, okay? So what we're going to give up is some amount of resolution. So we're going to coarse grain our configuration space into what we call states. So think about it as a kind of a big volume in configuration space that corresponds to all the vibrational excitations around a given topology. And then we're going to aim at generating a method that preserves the state-to-state dynamics. So in a statistical sense, if I look at my state-to-state trajectory that my method will generate, it should be statistically indistinguishable from what you would get by just coarse graining an MD trajectory over these big chunky states. And if we do this, then we lost no information at all about the long time behavior of the system, right? Because on long times, the system really evolves by jumping from these funnel to funnel, and that's what controlled the long time evolution. So if I capture this, then I'm all set. So I won't get into the details here, but the method we use to parallelize the dynamics in the time domain in a way that we're not subject to strong scaling issues is called parallel trajectory splicing. And conceptually, the idea is very simple, is that I cannot run a single simulation on the whole machine, but what I can do is to run a large number of simulations independently from one another. And if I do that in such a way that I can splice the pieces together to get at a very long trajectory at the end, then I achieve my strong scaling goal. And so far that I don't have any kind of leftovers left at the end of the run. Right? If I consume all of the pieces of trajectory that I generated, then I have a strong scaling solution. So we have to find a way to do that efficiently and accurately, right? We want something that provably gives you accurate results and not just arbitrarily butchers your trajectory. So that builds upon years of work by Art Voter and collaborators, where we really designed a suite of tools the formal tools that you might reach out to in order to generate these long-time methods. So again, the details are a bit technical, but in the gist, the idea is that we do have a procedure to prepare these pieces of trajectory in a way that they can be spliced together. That costs some extra overhead to do this, but you can show formally, just mathematically, that for a linear increase in the overhead that you're paying, you're getting back an exponential increase in the accuracy of the system. So you have a knob that you turn that controls how accurate your simulation will be, and that in counterpart controls how much overhead you'll have to pay. But you have this linear cost versus exponential improvement that is really weighted in our favor. So if you prepare these trajectories according to the special recipe that I'm not telling you the details of, you can actually splice them together on a state-by-state basis, just like what I had in the cartoon. So as I said, to get strong scaling, you have to decide what simulation you're going to run in real time so as to minimize the amount of leftovers that you're going to leave on the table by the time you're done. And there's a lot of work that goes into doing this. We use very aggressive bookkeeping. We use speculative execution, where we try to forecast what's going to happen in the future in order to continuously adjust which state we're running on to minimize the amount of leftover. So here I really want to call the contributions of Andrew Garmin. He was a student and now a postdoc with us, who did a lot of work on actually making the method efficient by playing all of these forecasting and bookkeeping tricks. There's also a big computational infrastructure under this, of course. But today, I will try to focus instead on the science and not tell you too much about how this is done. If you're interested, please come see us at the poster. Okay, so I'll just spend a few minutes talking about one application. So that's an application we're carrying out under the support of SciDAC. It's a partnership between Fusion Energy Science and Asker. So in fusion, you're fusing hydrogen isotopes together, and you're producing helium and a neutron. And if you do that reaction in a confined enclosure, then you can harvest the neutrons, turn their energy into heat, then steam, electricity, and then off you go. So we're working on the material science side of the project, not on the plasma side of the project. And we're especially interested in this region of the wall that's called the diverter. And this is kind of the vacuum cleaner of the plasma, where you want a region where you will direct your helium ions towards so that you can suck them out, as well as other impurities, so that you can keep your plasma in optimal conditions. So the problem there is that you have a big flux of helium that hits your surface, and that gets into the material and creates a big mess. So here you have an example of a surface of tungsten that gets exposed to a plasma, and you have this kind of shag carpet of nanotendrils that form on the surface through exposure to the plasma. So that's not good because you can create dust. It changes your mechanical properties. It changes your thermal conductivities. So you really don't want the microstructure of your material to drastically change when you turn the reactor on. So the life cycle of helium in a material is quite complicated. It's implanted in the wall at kind of low energy. So it just gets in a few nanometers in, and then it starts diffusing around. And when initially they diffuse as what we call interstitials. So they live in between the atoms of the tungsten lattice. And at some point, if enough helium atoms just encounter one another, they form these clusters. And now the local pressure is high enough that they want to kick a tungsten atom out of the lattice and then just collapse in the bubble. And then these bubbles can grow, emit defects like dislocation loops, and really mess up your material in a general sense. So here, what I'll focus on for a minute or two is the behavior of these nano helium bubbles that form when these helium atoms decide that they're unhappy enough living as interstitials and they have to kick an atom out. So if you look at the literature, the consensus is that once heliums are substitutional, so once they fall into a vacancy, they basically stop moving. So a few years ago, we had access to the Trinity machine at Llano. So we were able to run par splice on up to 100,000 cores. So we were able to set up these little bubbles and run them to very long times and see what happens. And again, if you do this with MD, you see that nothing happens. The bubble just sits there forever and nothing interesting happens. So what we found is that actually the bubbles don't move, but the materials around the bubble moves. So if the pressure is large enough in the bubble, it can kick a new tungsten atom out of the lattice and create a new vacancy. And now this extra tungsten atom is elastically bound to your bubble and can diffuse around and eventually zap back one of the vacancies. And if it annihilates a different vacancy than the one that created it in the first place, you see that the net effect is that your bubble moved. So at no point did an actual vacancy or containing helium atoms actually moved in the material, but the material just moved around the bubble in such a way that the bubble can do a random walk. So using these methods, we were able to characterize the speed at which the bubbles move as a function of the helium concentration and found that it's quite complex, right? If you don't have enough helium to punch a tungsten atom out, the cluster will never move. If you have too much helium, you're going to punch too many tungsten out, and then they form a little cluster by themselves, and they're happy. They're not annihilating. But in the middle, there's a sweet spot where these defects actually move very quickly. So what we did is that, well, quickly on engineering scales, right? They move very slowly on MD timescales, but as far as an engineer is concerned, they move quite fast. So to show this, we put these mobilities into a mesoscale simulation code that simulates how much helium is retained in the wall of the reactor and just turned on or off the mobility of these bubbles. And we can see up to 10-fold variation in the predicted retention of helium in the wall just by adding this, something that might look like a microscopic detail. And this comes from the fact that once the bubbles can move, they can move and just hit the surface and merge with the surface and just release their helium back into the plasma. So that's an example of things you can do with this code. We did a bunch of other things like looking at plastic deformation of nanowires. We looked at shape evolution of nanoparticles, did a lot of radiation damage. So there's really a lot you can do with these tools, and especially to look at the slow evolution of the material in a way that just wouldn't be accessible with molecular dynamics at all. So I don't have to go through the conclusions, but as all the teams, Exascale really is promising for us, but it also creates challenges, especially in fully exploiting this whole simulation space in length, accuracy, and time. And that really requires developing a new thinking of how you can map your physics problems into the machine so that you can get good accuracy. So I want to acknowledge the team again. It's really a team effort, and it's been just a joy to work with everyone. And I'm going to take any questions if you have any.
Fantastic. Thank you, Danny. Let's open it up for questions for Danny first. If you'd like to raise your hand or just unmute and ask, feel free. All right, looks like Reed has a question. Go ahead, Reed.
Hi there. Hi there. Great presentation and great presentations from all the presenters. I had asked the same question to the other two presenters, so I just wanted to ask you, Danny, as well. Were there other ECP teams or projects that helped you make these achievements? I know that like within your own team, it's quite diverse, but I was curious about if there were other collaborations within the ECP that kind of made this all possible.
Yeah, so I think a very important collaboration for us has been with COPA. So we collaborated, and actually now we have team members that cross both projects. So we had the slides that I skipped on performance optimization turned out to be really important to have a broad set of inputs to the problem. So we ended up having to rewrite the code from scratch in a proxy app that we were able to rewrite the different loops in different order, different memory access patterns, and so on. So we greatly benefited from collaborations with COPA. And we also use some of their solvers for the quantum, semi-empirical quantum methods that I didn't have time to discuss today. So we also work with SZ for compression. So they developed some nice compression schemes that were specially optimized for MD. And there will be a session tomorrow on compression where we'll say something about this. We worked with Veloci for checkpointing. What else? I think I'm forgetting something, but yes, I think COPA would be our central one, and then we had more data-oriented collaborations also with DST teams. Like COCOS, of course, right? A lot of our acceleration is done based on COCOS, so that has been really central to us.
Oh, great, thank you.
Danny, I thought you did a nice job of explaining why MD doesn't naturally strong scale due to the communication wall. But in my experience, there's also the IO wall where people who are trying to dump everything out also hit the issue that you spend all your time writing to disk and not computing.
Yeah.
How do you, with your new approach, how do you decide what to save of these replicas? And is it a bottleneck for you right now?
Yeah, no, so our obsession is on the rare events. So we basically really focus systems that evolve very slowly. So we don't need to save. So we have implicit in this whole machinery to splice segments together is that you're able to detect when you left one state and entered another state, right? So we only have to save one representative configuration by state, and typically that's the local minimum of the energy in that chunk of volume. So the first time we encounter that state, we save it. And anyway, we need it in order to be able to reinitialize more MD simulations from that state later on. But we don't need to save any kind of intermediate frames. So we already have a transition detection built in that's telling us whenever something interesting happened, and we just dump these guys. And typically the dynamics in our potential energy surfaces are quite slow. So you're going to vibrate a long time before you jump. So we're really compute bound on this. We're not having to save all that. I mean, in a big run, I might visit like 1 million different states, but that's still not a huge amount of data. So we're not bound by IO. So you would be bound by IO if you push along the weak scaling axis, where basically your memory is full of atoms and you need to dump all of them all at once. And in our case, the IO is asynchronous also. So there's an intermediate in-memory storage, and then that trickles down to disk in the background. So nobody has to lock waiting for IO to complete.
Thank you. That makes sense. Let me open it up to questions for any of the speakers. All right, well, I want to thank you all again. Again, fantastic first session. I really enjoyed all 3 presentations, and I appreciate the work you put into them. Thank you all for attending, and let's virtually thank all 3 speakers one more time before we adjourn. All right, thanks all. I'm going to close this one.
Thanks.
Have a good day.